My name is Huan, and I'm glad to have a presentation here for our paper, Soft Expert Reward Learning for Vision Language Navigation. I'm from the University of Adelaide, and the authors of this paper are Huan Qiu and Chunhua Shen. And here I'll give a brief concept of VLN task. It defines a simple task that agent is randomly spawned at a new environment. For example, like a start point here, try to find the correct path to reach the goal eventually. And more intuitively, you can see from the GIF figures here, a natural language instructions will be given to guide the agent to reach the goal. And current visual language navigation task models rely much on behavior cloning that treats expert behavior as strong supervision signals. That you can see from the table 1, that every agent except the random agent adopt behavior cloning, but it has problems by only using the behavior cloning, because behavior cloning enables agent to gain better performance on seen environments. However, agent may meet trouble on unseen ones due to error accumulation. Since the sequential decision problem, acceptable errors may accumulate at each step. Some models adopt reinforcement learning along with behavior cloning to overcome the error accumulation problem. Also from the table 1, you can see that several methods using reinforcement learning to conquer the aforementioned problem, but only design reward functions for certain functionality. So we call reward engineering here. By using the reward engineering only, it also have problems as well. Reward functions designed one environmental task may not generalize quite well to other scenarios. In some practical and complicated tasks, it's hard to define a reward function as game scores. In a game, it's easy to define a reward function, right? Because game scores itself can depict the how good the agent's behavior. And for some tasks, for example, like self-driving vehicles, you can engineer a reward to let the agent stay at the central of the lane to avoid collision with other vehicles. But it's hard in some scenarios to define the reward. In our paper, we actually have 3 main contributions. We propose the soft expert destination formulation. We shorten as SED here, which is simple yet offers effective reward signal to obtain expressive navigational ability. The SED reward encourage agent to have better alignment with expert in a softer manner. I will talk later in detail. We introduce another complementary reward signals along with aforementioned SED reward, termed as SP reward, to push the agent reach the destination as fast as they can. And as a result, we also show the performance of our model. It beat the current state-of-art methods in both validation set and testing set. This is the framework of our soft expert reward learning. In our model, we actually divided the processing path into 2 parts: a supervised learning branch and a reinforcement learning branch. And we actually introduced 2 novel reward functions here that we marked with yellow stars in the figure, which is SED reward and SP reward. So our contribution mainly concentrate on the reinforcement learning branch. In this branch, we use actor-critic algorithm as our reinforcement learning method. And for the reinforcement learning loss, actually, it consists of actor loss and a critic loss. For each RT bar here represents the discounted reward. So for each RT bar here, it calculated by the next RT plus 1 bar, multiply discounted factor with n plus the instant reward RT here. And for instant reward, actually consists of 3 parts, and the trade-off factor are provided to have a trade-off between different reward. And this is an encoded-decoded structure of our SERL model. after fetching the visual features and language features, it actually have a cross-modal attention to have better cross-modal attention representation for the later action selection and reinforcement learning branch updating. For the soft expert destination reward, intuitively, a higher reward should be assigned to an agent who take his actions close to the expert demonstrations. So besides the behavior cloning, we introduce a soft expert module, a destination module. It consists of a weight-fixed random network and a destination network. So in the training phase, we only input the expert demonstration for the destination network to fit the randomized network. So in this case, the distillation network could fit quite well in those expert demonstration data points distributions. So in the training phase, we choose the loss function like this. So for each data point, it consists of visual features, language features, and current action that taken. Well, in this case, a strong density function was formed. So using this density function in the inference phase, we input the agent's behavior when we try to actually train an agent, a navigation agent. If we use the similar formula to calculate the distance, SED distance. If a SED distance is smaller than a certain threshold, it represents the agent's behavior close to its expert. Otherwise, it means dissimilar actions would be taken. So positive reward and negative reward would be assigned accordingly. For the self-perceiving reward, our model will predict distance improvement ratio at each step as current schedule information. And we take one more step ahead by using this schedule information as another intrinsic reward, which we call self-perceiving reward here, to push the agent towards goal as fast as it can. So it offers more information than a raw distance change. And here is the performance evaluation. We actually bolded the best performance each column, and the upper part is the model without data augmentation. And we also follow the previous work. We perform data augmentation, have more instruction data to further boost the model performance. And you can see from the table, in most cases, our proposed SERL model have the best performance. And this is the ablation study. And for from the table, that we can see, we try to verify each components of our model. That from the table, we can see with every proposed model in our proposed components in our model, that our model could receive the best performance. And in the sensitivity test, you can see we try to verify the trade-off factor of alpha and beta. Our model shows the stability by changing the different alpha and beta. And this is a visualization experiments. Compared to the baseline model without our proposed reward functions, the baseline model pick the incorrect path towards its goal because of the error accumulation. But for our model, with the proposed to novel reinforcement learning reward functions, it could pick the correct path towards the goal. So that's it. Thank you for your time.